today for our very special colloquium of our very first Early Career Alumni Award winner. So I'm thrilled to get the chance to introduce Dr. Claire Pettersen from the University of Michigan, who mentioned that it was roughly 8 years ago to this date when her PhD defense presentation was in this room. And so you're not having that nightmare where you never finish school. Just you're back. So anyone who knows Claire knows that she brings her whole self into every collaboration and interaction. And I knew this from the very first time I got to interact with her as an eager participant of my meteorological measurements course in a year when I took the class of students, including Claire's Storm Peak Lab in Steamboat Springs, and where she was as much a student as a colleague on that trip. And that was just the start. Her drive has led to enormous early career success, currently as assistant professor of climate and space sciences at the University of Michigan. She holds a Bachelor's of Arts in Physics and Astronomy from Carleton College and a Master's of Science in Material Science and Engineering from the University of Wisconsin. She later found the correct departments by receiving her degree in Atmospheric and Oceanic Sciences with a Master's in 2014 and a PhD, as we mentioned, in 2017, advised by Professor Grant Petty.
And Rob Bernards.
And Rob Bernards, yes, thank you. And while at the same time working as an instrument innovator in Space Sciences and Engineering Center, both during and prior to that time. At Michigan, she leads what's called the Cold Precipitation Processes Group, which I think we'll hear a bit about today, where she focuses on cold season and cold location precipitation events, as well as associated cloud, thermodynamic, and synoptic characteristics. Her more than 40-plus publications and $9 million of grant funding is leading to exciting projects, including the NSF-funded Snow Sensitivity to Clouds in a Mountain Environment field experiment conducted jointly with AOS faculty like Angela Rowe and others. As this is our first time with this award, it's brand new, we were unsure what kinds of nominations we'd receive. We received many excellent, highly qualified nominations, but Claire's was the only one where we received 2 completely independent nominations. And I think a paragraph from one of those letters summarizes this best. Dr. Pettersen has a long history of mentoring students and her peers, producing a positive impact through the atmospheric sciences community as a result of her genuine passion for supporting other scientists. Take a pause from this letter. Raise your hand here if you have collaborated with Claire or been mentored by her or have mentored her or have co-authored a paper with her. That's a lot, right? It's pretty impressive just how widespread her interactions are. The letter continues. Dr. Pettersen's impact in the community has a far reach. Her energy and willingness to explore unfamiliar research areas and engage in cross-disciplinary research guarantees that her impact will only continue growing with time. And for all these reasons, Dr. Pettersen would be a model recipient of the UW-AOS Early Career Alumni Award. And so we thank you for being our model recipient as our first. Congratulations. I hope you saved room in your suitcase because you get to have this giant plaque.
Oh,
so we'll pass this on. Thank you.
The entire talk until my arms.
And a call for future Alumni Award winners will be going out in a couple of weeks. And so here's your model. Think about who else among our awesome alumni are
no pressure.
doing that. But today we're going to hear about high-latitude precipitation, perspectives from space and ground. And I'm going to turn it over to you. Thank you, Claire.
Thank you. That was such a nice introduction. I hadn't heard those letters. It's for those fellow Scandinavians in the audience, very hard to hear complimentary things. It makes me want to kind of hide. But no, it's really, really nice to be here. And I mean, this department has been, and space sciences as well, AOS and space sciences has been so supportive to me in my career. And I've continued to just build more and more networks and more projects with people here. So I couldn't be more honored to be here giving a talk and receiving this award, really, truly. So at the start of my seminars, I always give an introduction because I had a very non-traditional career path. I talked to the grad students about this a bit. So like Ankur said, I got a degree in physics as an undergrad, and then I got a degree in engineering, and then I worked as an engineer with Project IceCube. So this is me 20 years ago now, which is like, whoa, in Antarctica working on installing some optical modules to look for neutrinos as part of Project IceCube. So I was with them for 8 years, and then Fred Best and Hank Rivercombe, asked me to interview at Space Science Engineering Center to work on spaceborne instrumentation, doing engineering, which I did. I was very happy to join the group here. I came on working on Clario, working on some phase change materials. I also worked on various deployments with NASA and NOAA doing airborne instrumentation. And when I came to Space Science Engineering Center, after a couple years working with Fred, I sat down with him and said, I am really interested in atmospheric science. I would like to go back to school, if that's possible, when we're done with our first phase of Clario. Can I reduce my engineering percentage and then pay cash and go to school? And he's like, okay. Like, he was very supportive. And so that was awesome, and started my opportunity of working at the same time as doing my PhD. Actually, doing my master's, I wasn't convinced I was going to do a PhD. It took me a couple other steps and very encouragement from various faculty here. So I worked on the ice caps project. I went from ice cube to ice caps. So I went from Antarctica to Greenland, and worked on the ice caps project with Ralph Benartz, Dave Turner, Matt Shoup, and others. And most of my PhD work was focused on looking at cloud and snowfall properties over the Greenland ice sheet. And what's really nice is I continue this work with one of my grad students. I'm going to show some of her work, but our ice caps work has continued on. So I got my PhD in 2017. I had lived in Madison. I came here in 2001. I had lived here 20 years, and I was like, I'm going to live here forever. And I applied for the job at Michigan just thinking this would be a good exercise to organize my materials. And then they offered me the job. And so I packed up myself. I moved from University of Wisconsin and SSEC and AOS to the University of Michigan, where I'm now at the Climate and Space Sciences and Engineering Center, engineering building. So I've been there since January of 22. I have an awesome group of people, some of which you may recognize. So my group members currently, I have two researchers, Marion Maitling, who's here at Wisconsin, but we work together on GPM. Abby Hudson, who's a former postdoc and stayed on as a researcher in the Cooperative Institute for Great Lakes Research. She's a modeler and absolutely essential for our group. Fraser King just recently left my group, but I left him up here because he's joining you all here at AOS as new faculty in January 26th. So far, we've had 3 PhD students graduate from my group. Julia Shates, who many of you know here from University of Wisconsin, she's now at JPL. Tristan Renfree, from University of Michigan, who's now at Colorado State, and Yan Zi from Michigan, who's now at University of Oklahoma. And then currently our group has 4 PhD students, Jack Richters, who some of you might recognize from the AOS program, Alana Weedham, Anna Montoya, and Evan Barrett. And we also have a bunch of undergrads that work with us too. Really nicely, our group has lots of Wisconsin connections, so I thought I'd highlight these. We have a bunch of grads, including me. And we have Marianne, Jack, and Julia, of course. Alana, her spouse, was a grad here recently in computer science, and she really enjoyed UW and Madison. Abby Hudson is besties, conference besties with some people from she often shows up at our alumni event at AMS. And Fraser King, of course, is going to be new faculty here. Funny enough, when I was looking at emojis for teacher, I was like, wow, Fraser really looks like that emoji. So I was like, that's a little weird. But yeah, so we're continuing to build this network. Anna and Evan are new, so don't worry, we'll figure out ways to connect them to Wisconsin. All right, so what does our group do? Well, we work with precipitation observations. We've worked with several different ground-based instrument suites. I've marked some here: Great Lakes area, Alaska, Greenland, Scandinavia. We work with different spaceborne remote sensing platforms. I have GPM, CloudSat, and GOES here. And we're supported from different federal agencies. I have projects with NSF, NASA, NOAA, work a bunch with the National Weather Service. And we're primarily looking at wintertime precipitation, and often we're looking at snowfall. And I don't think I need to motivate a bunch of people in Wisconsin why winter precipitation matters, but just to remind you all, in a couple months, right? Snow affects our daily lives. Winter precipitation affects our daily lives. Maybe you wake up in the morning, you get out of your apartment, your road looks like this, you either need to dig out your car, you need to plan on the bus being 15 minutes late, right? It affects your daily life. And so we really want to be able to characterize precipitation for our local businesses and our daily lives. I love this picture. This was taken right before I left. This is the Beltline. This is a lovely echelon. This is pretty efficient snowplow removal. I think this was 2021. And all the traffic backing up waiting for them to remove the snow. But importantly, the better we characterize snowfall and winter precipitation, the more we can help stakeholders like Department of Transportation and states and cities plan for what they need. This is an extreme form of snow removal, this is the Upper Peninsula, which gets 300 to 400 inches of snow a year. This is in Marquette, and this is, you see your neighbor's little snowblower. This is the industrial size snowblower, and they actually need that up there because they have such large amount of snowpack. It, of course, builds our global ice sheets, right? Snow is the primary input into the Antarctic and Greenland ice sheets. And it changes our surface properties. It changes our surface albedo. Here's the Great Lakes region. This used to be focused on Wisconsin, but now I live here, so I have to say Great Lakes region. So before winter, at the beginning of winter, towards the end of winter, we have very different surface properties. We have very high albedo with the snow and ice cover. And when we think about the Mountain West, which is an area of study I've gotten more into lately, we have to think about planning for snowpack and water resources. And so this is the Sierra Nevadas looking in 2019 in February and 2020, and you can see the vast difference in the amount of snowpack in this region. Finally, it's not always snowfall we're worried about in the wintertime. A lot of places now in the high latitude regions are experiencing more rain in the place of snow. So if we think about places like Alaska or the Arctic, this was a really cool picture I found recently. Rain comes to the Arctic with a cascade of troubling changes. So we're starting to look at rain on snow processes as well. So hopefully I convinced you that we need to care about wintertime precipitation. And we have different methods of observing wintertime precipitation. A lot of people, when I give talks, are like, hey, can you just take a bucket out there and grab the snow and measure it? And it's like, yes, we can. They're kind of expensive buckets. They look like this. But a lot of things affect the accumulation and make for high uncertainty. For example, wind, right? And so the really gold standard of bucket collection of snow, or these weighing gauges, we put one of these buckets in the middle of this double snow fence gauge. These are about 5 meters across, and not easy to build. You have to maintain them. You can't just put these everywhere. You certainly can't put them in the ocean. And so that's one method. Another method is we can do these deployments where we take small profiling radars like what you see there, that little dish that looks like a TV dish, but that's measuring a profile of precipitation. We also have things called distrometers. We have laser and video distrometers that take images of what the precipitation looks like and gives us characteristics. So that's another way we can measure snowfall and rainfall. We, of course, have a big network here of radars. We have the NexRad radars, ground-based spatial radars telling us something about precipitation, giving us warnings, helping with forecasts. But what you'll notice here, even though we have really good coverage, we have these big blank areas in the Mountain West where we have a lot of mountains blocking the beam. We also don't always characterize well shallow precipitation, but it does give us another piece of information. And finally, you can't put a bunch of radars floating out in the ocean, so we have some satellite-based precipitation sensors. We have GPM and CloudSat shown here. I'm going to talk about them a little bit more. And we're building on these with missions like EarthCare and advancing our ways to see precipitation from space. So we have lots of tools in our toolbox. None of them are perfect, but they're all really useful, and we can use them together in really innovative ways. All right, so key question, our group. I wanted to do a really broad general question. Does categorization of events into various weather regimes illuminate key precipitation processes? Meaning, can we use general regimes to help us put some limits and better understand precipitation processes? And so how we do this is we leverage innovative combinations of ground-based and spaceborne observations. We also are evaluating precipitation macro and microphysical properties in the context of these environmental conditions, meaning the dynamics, the thermodynamics, et cetera. So I'm going to do in a really simple way, how do we think about weather regimes? I'm just going to give a brief example. It's not the only example, but I kind of like this approach, and this is a lot of what my group does, of doing these rough cuts of looking at general weather regimes and doing comparing and contrasting. So I got this from Stephanie. This was in your department, Stephanie Henderson, and it's just a nice way to visualize some different kind of large-scale flow. So on the left here, we have zonal flow. On the right here, we have a very disruptive meridional flow. The contours in yellow are 500 millibar heights, and the blue barbs here are 200 millibar winds. And on the left here, we have nice zonal flow from the US to Europe. The upper level flows generally going from west to east. And if you're flying from Detroit to Frankfurt, this is a really nice pattern to see right before you get on the plane. However, we're interested in extremes and how moisture is like moving meridionally. A lot of the work we do is looking at those weather regimes that affect a lot of air up to the polar regions or bring air down from the polar regions. So one way we can look at this, just very generally as an example, is we have this big anomalous anticyclone here. On the left side of that anticyclone on the west, we have this indication from the wind barbs and this disrupted flow of warm air advection where we're getting some indicator of transport of warm and moist air poleward. On the other side of this this anticyclone, we're looking at cold air advection where we're seeing transport from these wind barbs of cold Arctic dry air equatorward. So this is just very simply encompassing some types of weather regimes that our group looks at and uses this to look at uses as a lens to look at precipitation. So I amazingly want to show that my group's doing some awesome work. I am not going to go through all these papers, but just to look at some different categories, we do some comparing and contrasting, looking at when we have warm air advection versus cold and dry air advection, and we've got some really nice papers on varying comparisons of macrophysical qualities of precipitation, as well as some microphysical characteristics that we can link back to weather regimes. And I just want to highlight Fraser's papers here. He did this awesome kind of series of papers as part of my NASA NIP award, where we developed a data set, we used it in a statistical way, we used it in a machine learning way, and really you can take the precipitation microphysics and back out to various weather regimes. It's a really cool group of papers. I'm not going to talk about it at all, but hopefully when Fraser's here, he'll tell you guys all about those papers. Sometimes we just look at, for example, cold and dry air advection. We have several papers about lake effect snow. Recently, Abby Hudson just put together a really nice modeling paper about Great Lakes region lake effect snow, which occurs when you have cold, dry air masses going over relatively warm and moist lake surfaces and surface air. Marion Maitling, who's in your department, recently, a couple years ago, wrote this great paper investigating marine cold air outbreaks using CloudSat. And that's another way we were kind of using this general weather regime to look at the properties of the snowfall. We also look at these warm air advection cases. And I'm just, again, being really general, but we've looked at these in different ways. We've looked at when we have atmospheric blocks and how they bring warm, moist air atop the Greenland ice sheet and produce snowfall. We've looked at enhanced meridional transport in the Antarctic and Arctic. That's two of my former students, Tristan Renfrey and Jan Z. And we've also looked at an extreme condition of warm air advection, atmospheric rivers, which I'm going to talk about today, where we've looked in the Arctic, we've looked at from a spaceborne and ground-based perspective. All right, so what I want to talk about today is a couple recent papers where we focused on atmospheric river impacts. And what we found, I'm going to give you the punchline first, is that when we look at atmospheric rivers in the high-latitude regions, we see an increase in snowfall occurrence and rates. We see that they impact and change snow microphysics in very indistinct ways, and they can affect precipitation phase. So first off, what's an atmospheric river? With a crowd of meteorologists and atmosphere and oceanographers, I probably don't need to describe this. You've all probably seen or heard of atmospheric rivers, but they're long, narrow regions of the atmosphere that transport relatively high amounts of water vapor outside the tropics to the mid and high latitudes. And so we have this nice imagery from SSCC I wanted to feature that shows that atmospheric river coming off Hawaii and impacting the Pacific Northwest. When I give general talks about my science and research to kind of a broad community, I ask who's heard about atmospheric rivers to see who raises their hand, and then I ask them if they're from California or if they're from the Pacific Northwest, right? But what's interesting is 10 years ago, you didn't hear in the local news, you didn't hear people talking about atmospheric rivers, and you didn't hear them talking about heat domes. So I'm always curious, kind of when I talk to general audiences, broad range of people, what meteorological terms they're starting to hear more and more.
It's a new term, right? It
because
wasn't around 20 years ago.
Yeah, but I'm thinking not just atmospheric scientists, but who now it's talked about on the news, right? Now they have categories of atmospheric rivers, so it's interesting I think it's interesting kind of from a social perspective, and same with heat domes, right? It's yeah, exactly. So this is a figure. Now it's a bit of an older paper from almost 10 years ago, but a figure from Walser and Guan, where they were looking at the frequency of atmospheric river events with their own kind of detection method and seeing where they tended to occur. And so if we look in the high latitudes, I'm being a little generous here, but I like to say high latitudes are, poleward of 45 degrees north-south. We see the occurrence of ARs is often greater than 10% of the time. Furthermore, they used reanalysis products to say, when you have atmospheric rivers, how often are they associated with extreme precipitation? In this paper, they said the 95th highest kind of instantaneous rates or daily rates, I can't remember. But they showed that more than 40% of AR events in this high latitude region are associated with extreme precipitation. And all of this was done using reanalysis products. And we really wanted to explore this more from a satellite-based perspective. So I'm going to talk about several papers, just little pieces of all these. I know that's like an overwhelming amount, but I really wanted to feature all the great work people in my group have done. But we're going to talk about it from a spaceborne perspective and also from some of these ground-based sites. And all of these work have given us different insights into the impacts from atmospheric rivers and kind of all built on each other, give us different pieces of information. So for our detection method, I am not here to debate different detection methods. If you want to, Kyle's in the back, you can argue with him. Sorry, Kyle. But we use Kyle Mattingly's atmospheric river detection method from his 2018 paper. And this was specifically tuned for the high latitude region. And this is available calculated from MERIT 2. Additionally, Kyle's added ERA 5. And we have 3 hourly resolution from 1979 to 2024. So we have this nice database to work with. And what we've done is we've coupled that database with observations from GPM. So GPM is the Global Precipitation Measurement Mission. It has both passive and active microwave instruments. So the passive instrument is the GMI, which produces rates from a retrieval called GPROF, rates of precipitation. We also have an active microwave instrument. We have the DPR, the Dual Precipitation Radar, KU-KA band radars. It's orbitally inclined at 65 degrees, and I like to say this gives a high latitude advantage because you have this maximum revisit at 61 degrees. And when you think about where you have the population centers in the high latitude regions, there's a lot of people living between like 55 and like 63 degrees. Not a lot versus the mid latitudes, but you have a lot of population centers there. So this is work that was led by Marion Maitline. So I wanted to feature this nice data set we have with this accompanying paper from Earth and Space Science. So what you see here is we have the Mattingly ARs, those are in those magenta outlines, along with the swath from GPM, showing you the GPROF retrieved rates from the passive microwave. And we've collected all of this information from 2014 to 2024 over all seasons, over land and ocean throughout the Northern Hemisphere. And this is so we can look at things kind of in a composite sense, where we're comparing these times where we have atmospheric rivers versus times where we don't. So what did we find? And I can only feature a couple things, and I'm going to focus on all of these plots are going to be wintertime DJF in the Atlantic region. And what we find is this shows us the frequency of precipitation observed. And what that means is as a function of all available GMI observations. And on the left here, you have DJF wintertime precipitation when you have a coincident atmospheric river. And on the right, you have the no AR precipitation frequency. And just to remind people, this region has ARs between like 8 to 15% of the time. So unsurprisingly, we have more frequency of precipitation when we don't have atmospheric rivers. That didn't really surprise us. But something that was interesting, and just to orient you, I've drawn this line. We have an increase in precipitation occurrence happening at higher latitudes when we have these atmospheric rivers. So those atmospheric rivers are very efficient to transporting that water vapor poleward, which is resulting in some more occurrence of precipitation. So this is all precipitation. When we just look at snowfall, we see something similar. Obviously, we have less occurrence. We have it not occurring as much as the total precipitation. But again, if we put this line to orient us, we see that snowfall is occurring at higher latitudes, deeper into the Arctic, when we have an atmospheric river. So atmospheric rivers are causing snowfall to happen more often. And we don't just see this in DJF, we see this for all seasons. We also looked at the mean conditional rate of the snowfall because we want to know, if you're thinking about the impact of snowfall, you want to think, is it occurring more often? And if it does, is it more intense, right? So again, here on the left, we have wintertime AR snowfall rate, the average conditional snowfall rate. And on the right, you have the no AR snowfall rate. And what we see, it's pretty obvious here, we have much higher rates. This is from 0.1 to 0.75 millimeter per hour, liquid water equivalent snowfall rates. So we see enhanced rates when we have these atmospheric rivers. And I know these values might not sound like a lot, but when you're in the high latitude regions, this is a lot of water mass. So there's a bunch of other things we did, but I also wanted to highlight this other paper where we looked from a CloudSat perspective at some impacts of atmospheric rivers. So the CloudSat mission it's no longer around, but it had an active microwave radar, a W-band radar called the Cloud Profiling Radar, and we're able to get snowfall rates over land and ocean from that radar. It's orbitally inclined at 98.2 degrees, and so I say it has a polar regions advantage, right? It has a super high revisit over the global ice sheets, both Greenland and Antarctica, and it's really sensitive to snowfall and light precipitation. So one thing we did with this is my graduate student Tristan Renfrey was really interested in what's going on with cryosphere and ice shelves and was curious how atmospheric rivers would affect them in different ways. So he decided he wanted to investigate snowfall characteristics during atmospheric rivers, during enhanced water vapor transport using CloudSat over key ice shelves in the west and east Antarctic ice sheet. So those are highlighted here, those basins. And I'm just going to zoom in on a quick result. So this is the Pine Island and Thwaites ice shelves. These are a very dynamic area of Antarctica. And over here on the left, to orient you, we took all the snowfall rates from 2007 to 2011. Then we just took our cases where we had atmospheric rivers, composited them, and then differenced out the background snowfall rate to try to see what the change was when you had atmospheric rivers. And I'm just showing here fall and winter, so MAM and JJ in the southern hemisphere. I'm just showing these two seasons, but we saw this for all seasons. And the top here is as a function of percentage. And what you see is the snowfall frequency increases, that's that blue color, over these basins when we have atmospheric rivers. We see that blue color, and we see that stippling, which indicates it's significant. And this was 20 to 50% more frequent snowfall when you had ARs. And another thing we notice is it goes deep into the ice sheet. It's not just at the coastline. So we're seeing this, again, this indication that we're having this moisture is pushing a lot of that snowfall and producing snowfall at higher latitudes. On the bottom here, I'm showing, again, these conditional mean rates, and I'm showing that difference to the background of the CloudSat, kind of, not climatology because it's only 4 years, but that kind of CloudSat baseline. And again, we see a lot of blue. Our differences here go from 0 to 0.4 millimeter per hour, which is a lot of liquid water equivalent snowfall. And what we see, again, across all seasons for those basins, we see a lot of blue, and we see more than 0.1 millimeter per hour increase in the amount of snowfall when we have these atmospheric rivers deep into the Antarctic ice sheet. All right, so some key takeaways from the satellite perspective, from GPM and CloudSat about snowfall when we have ARs at these higher latitudes, is we see that more snowfall is occurring. We have more frequent snowfall at higher latitudes during ARs. And importantly, we see that these penetrate deep into the polar regions. Also, the mean snowfall rates during ARs are significantly higher than the non-AR events and can lead to extreme precipitation. All right, and these are summarized in those two papers there. I'll have a link to all the papers at the end if you're interested in a particular one. So that was from the satellite perspective. I said perspectives from space and ground, so now we're going to look at some strategic ground-based sites. And we're going to look at the snowfall characteristics that they saw during atmospheric rivers, but from the ground, with different tools and different pieces of information. And we're focusing on these three long-term sites, Marquette, Michigan, Hutula, Finland, and Summit, Greenland. Importantly, these sites have over 10 years of continuous observations at all these sites. They all have remote sensing and in situ information available. So they have profiling radars, some have microwave radiometers, distrometers, radiosondes, et cetera. So we can get a lot of various pieces of information about what's going on during atmospheric rivers. And this work was led by two of my grad students, Jack Richter and Alana Weedham. This is a very busy table, but I'm just highlighting these. Marquette, Hutula, AR snow, no AR snow. Basically, we see that when you have atmospheric rivers at these sites, you almost double the instantaneous rate when we look at all the AR snowfall events together versus the non-AR. Similarly, of course, swapped, the AR is on the right there and the no AR is on the left. We see a doubling of the average snowfall rate in Greenland when we have these AR events. So, and these were all statistically significant. So when we composite all these events together, we simply get these higher snowfall rates at these ground-based sites. And the liquid water equivalent is almost double. And these were all derived from either radar or disdrometer observations on the sites. Jack had some extra tools at Marquette and Hutula, and this is a very complicated plot, so bear with me. We'll just kind of mostly look at this line plot on the right. But he had a video disdrometer. So he had this imager that would count the number of particles and give you some size information. So we have Marquette here on the top, Hutula on the bottom. The y-axis is telling you something about number density, and the x-axis is telling you diameter. And the bottom line here is when he compared the AR snowfall events to the no AR snowfall events at these two sites, Marquette and Hutula, he saw that AR snowfall contained 40 to 50% more individual snow particles. So for any given event, you just had way more individual snow particles. And also, he found that AR snowfall has a higher concentration of snow particles no matter what diameter. So it wasn't just small particles and it wasn't just large particles. You had more particles at various sizes. And this was at both sites where you have this AR versus no AR, red versus blue. So we know we have a higher number concentration. We also wanted to know something that would indicate some details about the growth processes. And so another thing we looked at with the disdrometer was the vertical velocity of these particles. So we looked at the fall speed distribution. So we have fall speed here, Marquette and Hutula, diameter here, AR is red, no AR is blue. And what we found at both sites, when we had the AR events, all sizes of particles fell faster during an AR event than no AR. And so what this is indicating, we also looked at density distributions, but basically you have denser, faster falling particles of snow when you have an atmospheric river. And we did some modeling and some comparisons of some earlier literature, and it actually indicates that we have about 10% more rhyming when we have AR snowfall, where rhyming is the accretion of supercooled droplets onto ice particles, so it really increases the mass of the snow particle quickly, and then it's just gonna fall out that much faster. So this gives us some information about what processes might be like taking all of that extra available water vapor during the ARs and converting that into deposit or condensed mass.
Does that extra water vapor come with extra nuclei?
Oh, that's a really good question. I think so, and I think for places like, and actually in Greenland, my colleague Heather Guy did it, looking at that, especially like a place like middle of Greenland, you don't have a lot of IMP, right? And so she found that we would have a lot of coincident either blocking conditions or AR conditions that had a lot higher aerosol concentration. So yeah, and we are able to decouple some of that. We looked at dynamics, we didn't have that, but that's absolutely a valid question, for sure. Yeah, or maybe we're just getting more secondary ice production. Maybe you're getting, because they're windier conditions too, if you're getting ice crystals ramming into each other, breaking apart, now you have more IMP, right? So it could be all that. Yeah, thanks. Similarly at Summit, so we have a different suite of instruments at Summit, but we have a lot of tools in our toolbox there. So Alana Weedham led the study. I'm just going to show you one tiny piece of it. But she looked at atmospheric river vents going all the way up to central Greenland. And one thing she found simply is that every time you had an atmospheric river within 200 kilometers of Summit, you had snowfall at the site. The reason that's exciting or significant is it's actually really hard to have snowfall occur at Summit. You think, oh, well, you're on this giant, mound of ice. Well, it's a very cold and dry place, so it doesn't snow that much. It's essentially a desert. So all of the AR events produce snowfall at Summit, and importantly, what she shows here in these box and whisker plots, this is snowfall rate, this is a function of month. So some months we have very low number value of individual events. But even overall, you see significantly higher rates when we have ARs than not. Effectively, they're doubling that daily average snowfall we would get. We did not have a disdrometer at the site, which is kind of a bummer, but we do have some of this ancillary bits of information that can give us some insight into snowfall microphysics. So we had the multi-angle snowfall camera. There are a couple different summers, I think 4 different summers, which takes these pictures from 3 dimensions of ice crystals. Also, we had the ice particle imaging camera, which you could grab a slide and you had a camera on a microscope and you could get these really nice pictures of crystals. And what she found, we had for about over half the AR events, we were able to find imagery. And what Alana found is that anytime you had an AR event, we had presence of rhyming, so this fuzziness that you see, as well as dendritic growth processes, so these nice dendrites. Why that's important? In a place like Summit, Greenland, that's super cold and dry, you mostly have pristine crystals and you mostly have like bullet rosettes and plates. It's pretty unusual to get dendrites and rhyming. So again, it's telling us maybe when we have these atmospheric river conditions, we're getting more indication of rhyming, more indication of having some dendritic growth. All right, so their papers have a lot more information in them, so if you're interested, please ask me or talk to them. But from these long-term sites, the ground-based sites, we found, again, the mean precipitation rates during ARs are significantly higher than non-AR events, the mean snowfall rates. And importantly, some of these microphysical observations that we're able to do at the ground that we can't do from space indicate higher number concentrations of snow particles, denser snow, and increased aggregation and rhyming. So we have some snow process information from these studies. All right, so I'm just gonna say some stuff we're working on now. This led to some curiosities, that's the fun part of science. I sometimes move on to the curiosities too fast before closing stuff out, but that's okay. But we got really curious about what was happening from all these other observations we saw during these events. We saw that atmospheric river events at these sites we were looking at were associated with increased temperatures. That's not really surprising, but the criteria we're using is water vapor and winds. We're not using any temperature information. So just to convince you all, Jack and Alana's paper both saw really high increased temperatures from temperature increases from 3 to 10 degrees Celsius. These are local observed 2-meter temperatures from these sites when we had AR. So when you have an AR come in, those surface temperatures were increasing from 3 to 10 degrees C on average. We also saw these increases regionally. Both Jack and Alana were curious about the large-scale flow, so we looked at geopotential heights, we looked at IVT, we also looked at temperature anomalies. So these are from reanalysis products from ERA 5. Marquette and Hutel are at the top. The temperature range here is brown means an increase in temperature, blue means a decrease. Alana looked at Greenland, Summit, red is an increase, blue is a decrease. And what you notice with the locations here, the gold stars, black star, all of these saw a big increase regionally in temperature. These composites of reanalysis surface air temperatures also show increases from 3 to 10 degrees C. So we're getting this, we're producing snowfall because these places are cold, but we're seeing these big increases in temperature. Finally, we also had the ability to either use reanalysis or radiosonde observations to see what the profile looked like, our temperature profile. Our temperature, and we also looked at the water vapor profile. But here's Marquette and Huetela, AR and no AR, red and blue. Summit here, that red dashed is when we have ARs. The black is kind of the snowing time. Sorry, the yellow is the snowing time. It's hard to see. But what we found, again, that we had mean profile temperatures increasing 2 to 10 degrees C, and importantly, these increases persist throughout the column. You can really see it in the Greenland data. So we have this big increase regionally in temperature, locally at the surface, and deep into the column. Okay. So not surprising, I already told you we're looking in our warm air advection, my very, very, rough categories. So this wasn't wholly surprising, but it got us thinking about precipitation phase. We said, okay, these studies I just showed you all focus on snowfall and frozen precipitation, but we wanted to know what's going on with precipitation phase. And in fact, anytime Alana gives a talk about her Greenland work, inevitably we get questions, what's happening at the edge of Greenland? Is it raining? Is it snowing? Because that has big implications for the ice sheet. So Marion and I are working on this, and Alana's working on this too, but I'm just gonna show stuff that Marion and I are working on. So now we're looking in that same region we were looking at before. We are now using the GPM radar, the DPR, so the dual precipitation radar. And instead, we've changed to an occurrence. So now we're seeing the difference between AR minus no AR, where the AR events are the greener and the no AR events are blue. And what I'm showing you here is the conditional occurrence. So if there's rain, how often does it occur when you have an AR and versus not, okay? And what we see, and this is again DJF, we see increased rain occurrence during ARs It's shifted to higher latitudes. It's pretty obvious. I didn't add a line here. It's kind of, you can see it. I'm just showing the Atlantic sector, but we see this both in the Atlantic and Pacific, and we see it for winter and the shoulder season. So we see it for DJF, we see it for MAM and SON. We don't see it in JJA. All right? This is interesting because a separate paper a year ago from my student Yan Z, completely different focus. She's like, I'm really curious what happens to surface albedo when we have rain on snow events. I was like, cool. Okay, we just need many, many years of rain on snow events. So we used the North Slope of Alaska site. We looked at 10 years of data, and we got a bunch of different rain on snow events for different months. And what she found for her rain on snow events in May, so in the shoulder season, and she wasn't focused on this, but when she was looking regionally at what the large-scale conditions were, she found that during all those events, now this is a composite of 30 events, but she found that you had indications of IVT, enhanced IVT, coming from lower latitudes right up here to the site. And when we looked at how anomalous that water vapor transport was, we found that was highly anomalous, and this whole region had kind of 95th percentile of IVT. So this is indicating extreme transport from lower latitudes, and it turns out a lot of these are atmospheric rivers. So we started from the albedo rain on snow perspective, and we found this. Interestingly, when she looked at June, no anomalous transport at all. The rain events were all this like local kind of normal thing, which really agrees with what we found here, that we didn't see this increase during JJA. Another thing we wanted to look at is, can we get some information about the precipitation microphysics from the spaceborne platform? And we can. And one thing we're doing is looking at what's called the level, the bright band, or the level in the atmosphere where we see the snow melt into rain. And so I think everyone in this room is aware of this, but the majority of rain, and I would say the vast majority of rain in the mid and high latitudes, starts as snow and ice. Okay? So at some point, it falls through warmer and lower altitudes, and if it becomes rain, it has melted on its way down. And so we can use that bright band signature in radar as an indicator of a melt level. So this is just like a brighter layer of reflectivity. So we can say that's the level it melted in the atmosphere. And this is something people have looked at. This is a Prine and Heimsteel paper from 2020. And they importantly found that like as our global temperatures are warming, we're getting higher and higher melt level heights, right? We're getting a deeper, warmer column, so the melting's happening at a higher level. So we wanted to explore this melt level during the ARs to give us some insight into the precipitation processes, right? I'm just putting up Alana's figure here where we saw this composite of all of the temperature profile radiosondes during ARs are over here in the red dashed, and snowing's over here in the yellow. You see that almost 10-degree delta. We have this warmer, deep warm column of air. So we expect that we'll see higher melt levels during AR events. Now, I will caveat that this is valid for these are stratiform events or relatively low convection events. And in the high latitudes, a lot of our rain tends to be stratiform or low convection. And so what we find here, again, sticking to wintertime because it's just easier to stay with the same season. We have AR melt level bright band height on the left, no AR bright band height on the right? So that's indicating our melt level. And 1 to 3 kilometers there, and you can see a lot more yellow when you have the AR characteristics. So that deeper column is actually making those particles melt at higher in the atmosphere. If we look at this instead of spatially, we look at this as zonally. So the dark blue and dark red are DJF, AR, no AR, respectively. The light blue and pink are JJA, AR, and no AR, respectively. Y-axis is bright band height, and this is these zonal averages by latitude chunks. And what we see is we have a higher melting level during AR events across all latitudes for all seasons, including JJA, in both the Atlantic and Pacific sectors. So interestingly, we don't get more occurrence of rain during AR, but we still get the higher melt level of the rain that does occur. All right, so what we know so far, again, this is evolving, and I'm writing this up with Mary, and I'm going to submit it soon. We see more frequent rain occurring in the higher latitudes during AR, with the exception of JJA, our northern hemisphere summer. And I don't know the answer to this. I'm thinking about it. Is anomalous warm air not needed? Are we just kind of at a higher threshold so we don't need to bump above it? I'm not sure. We're kind of digging into what we think is going on there. The deeper column of warm air that we saw in all those ground-based studies that's coincident with ARs increases our melt level height. We see evidence that across all seasons, we see an increase in the melt level height of the precipitation. So that's pretty exciting. We're excited to write this up. I'm happy to talk to people about it because it's still like in that formation phase. So that's a lot of what my group's been doing. I wanted to highlight all their stuff, and it would have been even crazier than this talk was. But hopefully you got intrigued about some of the stuff my students are doing. So again, we've worked with these long-term sites, field campaigns. I want to talk about really quickly some future planned efforts, because I'm not going to go over I'm at minute 41, so I don't want to take up too much of your time. But have a couple future efforts. I am building up a suite of instrumentation at the University of Michigan Biological Research Station. You are all welcome to come hang out there. It's really cool. Building up a suite of instruments. We have profiling radar, microwave radiometer, LiDAR. We're going to have like a mini ASR arm suite there. So I'm working on that, getting that installed. I'm also a fellow with a German Arctic consortium called AC3, and we have a mini campaign in Svalbard planned for this spring, winter, and a longer one next winter. We're hoping to coordinate with Nurture on that, which is a big upcoming NASA flight campaign. I have to talk about snow climbing because that was my entire life for the last year, and a big effort, and included a lot of great people from University of Wisconsin. So with my last couple minutes, I just want to highlight some fun stuff from snow climb. You can talk to people like Angela in your department more about this, but the idea with snow climb is we really wanted to connect large-scale flow to these mesoscale effects, to that microscale, what ended up happening to the snowfall under these different conditions. And this was a statement from the proposal, and I crossed it out because we did it. Snow climb collected complementary in situ and remote sensing observations of thermodynamic, aerosol cloud, and precipitation conditions with coincident mountain surface observations to evaluate the macro and microphysical cloud and snowfall properties over entire accumulation season. And that season was December 2nd, 2024 to April 15th, 2025. And I was out there the entire time with the exception of the week the UW students were there, so I'm sorry I missed you. I was in Finland. Just to give you an overview, this project is under this new umbrella where you request NSF community instrument facilities, and so they have base funding for these community instrument facilities. Spark is one, right? And so we requested some of these, not Spark, sorry. We requested CSU C-Pol, which is the seagoing polmetric radar. It's a C-band Doppler dual polarization scanning radar. And it was based here out at the Yampa Valley Regional Airport. Just for some perspective, Steamboat Springs is here, and it's right here in the US. We also requested another radar. So C-Pol is a precip radar. This is a cloud and precip radar, the Ka-band scanning and polmetric cloud radar, Casper. 35 gigahertz Doppler dual polarization scanning and profiling radar to give us information about the valley. C-Pol is giving us the regional information, and Casper is giving us that valley information. And both of these radars would stare at Storm Peak Lab here on top of Mount Warner. Onkar alluded to I went to Storm Peak Lab as part of his class, and I was like, I should write a proposal to do a field campaign here someday. And so it happened. We were very lucky. But what's cool about Storm Peak Lab is it has all these key in situ observations of cloud, snow, and environmental conditions. And importantly, if it is snowing in the valley, where you're at C-Pol, you're at Casper, Storm Peak Lab is 90% of the time going to be in cloud. So you're like an aircraft just sitting there in the cloud and letting you pass over you, getting that Eulerian point of view. So we have a whole season of data. So the main question I get right now is how to go. Well, we all survived. We had a good safety plan, no injuries. Everybody was happy, but importantly, we can't control, you plan a whole field season and you can't control the weather, Well, contrary to what you might read on the internet, you can't control the weather. Okay, so we were really lucky that we had 302 geometric inches of snowfall measured on the mountain. The mean is 307, perfectly happy with that. In fact, if we had a really active season, I probably would not be here giving a talk. I'd be have quit my job and run away somewhere. But we also had one of the highest snow water equivalents of the entire interior west. It was a really dry season, so this was a little nerve-wracking, so we got all this. We did 22 IOPs, intensive operational periods, which included not just the radars, but all kinds of other instruments, including radiosonde launches. We sampled a large variety of storm systems, rhymed pristine aggregates with snow, different wind directions and magnitude, varying moisture and temperature conditions from very dry to possible atmospheric remnants. We had over 60 people on site in Steamboat for various durations of time. This was from University of Michigan, Utah, Washington, Wisconsin, CSU, Stony Brook, ProSensing, NCAR, Purdue, CU Boulder, University of Puerto Rico, University of Hawaii. 22 of these people were graduate students, 11 were undergraduate students, CSU plus students, plus the class from AOS. And importantly, 20 of these people, this was not their main project, and they gave us their time and efforts, which was really appreciated. They also got to ski for free, but they had a lot of other important duties too. So here's some pictures from some of the folks. We have lots of pictures of the campaign. And so I just wanted to tell people about snow climb, and you should ask Angela as well as other people here, Sarah, for some insight into snow climb science as we're developing stuff. Since this was alumni talk, I wanted to give one final thought about my career and kind of like how I ended up where I ended up. When I was at Carleton in 1999, I saw a seminar. We had this seminar series called What Physicists Do. Professor Walter Tape from University of Alaska Fairbanks came and gave a talk about Antarctica, Greenland, and atmospheric halos. He wrote the book on it. He's a mathematician that wrote all the angles. I think he has one called The Search for Angle X or something. So when I was 22, my brain was like, I'm going to Antarctica. No one can stop me. I'm getting on an ice sheet. This talk directly led to my interest in Antarctica and field work. But I think subconsciously he planted like something in my brain that like, wow, this is really cool. Ice clouds are cool. I was thinking about ice clouds in the back of my head for many, many years. And, that kind of came back around. My PhD had a lot of ice cloud work. And mostly what stuck with me is how much I appreciate the beauty. And I always have students look at the optics picture of the day and send pictures of clouds. And Angela and I talk about this a lot because it's so fun. We share cloud pictures. I was just amazed at how beautiful clouds are. And I just want to remind people that that's a perfectly acceptable and good motivator to do the work you do. Like, if you think tornadoes are cool, or weather forecasting is fun, or clouds are pretty, that's a really good reason to do science in that area. So I'll just leave you with that thought. And thanks so much for your time.
A few minutes for questions, and by tradition we ask for student questions first. Open the floor first to students. Jump in.
Yeah, amazing talk.
Oh, thanks.
For your GMI and GPOF project, how did you deal with the uncertainties that using a passive sensor gives you for precipitation?
Great question. And actually, we applied it to version 5 and applied it to version 7, and a lot of stuff changed. Mostly in the non-air snowfall, because shallow snowfall is so hard to detect and stuff. So I work with Sarah Ringerud. She's part of this project. She's at NASA Goddard. And we've propagated through a lot of those uncertainties. And you're welcome to talk to Marion about it, too. We thought about this a lot. But of course, we're dividing things into physical, AR versus non-AR. So are we inducing biases or something like that? We do think the GMI is missing a lot of the shallow snow in the non-AR, because when we look at the DPR, the radar data, AR looks the same, and non-AR has a lot more snow. And we think that's the shallow snow. So that's something we've been working with Sarah on, trying to we do have some caveats in the Earth and Space Science paper about that, but that's something we definitely are concerned with, because when you're categorizing stuff, you're automatically could be wholesale missing a chunk of snow, and we think we are. So that's why we're adding DPR, and actually Jack's next paper is he's using airborne and ground-based OBS to try to like connect back to the satellite. So we're hoping that will give us some insight. So we're using the general uncertainties that are there in the GPROF product, but we certainly have some like, wow, in this situation it works pretty well, but this situation I think we're missing stuff. So great question. So if you want to use that data, it's publicly available on Deep Blue, and you can read the paper, and then you can talk to us, and we're happy to help you with any caveats and stuff. Sure.
Yeah, great talk. One thing that came to mind, so I was interested that you were looking at atmospheric rivers over, I think it was in Lansing, you had a station?
Oh, Marquette.
Marquette.
Yeah.
And I've seen a lot of stuff about atmospheric rivers, and really not a lot of stuff about atmospheric rivers in the Midwest. So I was wondering if you saw anything that was really different or unexpected, or if you think that there's science on atmospheric rivers to be done in that region.
Yeah, and a great question. Actually, Zach Siriano is doing more papers on this. Marion did a nice ground-based study earlier that kind of set some of the groundwork. Microphysically, what Jack and I were really surprised at is that we had a lot of consistent microphysical story between Finland and Marquette, and the pathways are really different. When you have an AR coming Marquette, it's coming up from the Gulf and like that moisture conduit. And when we did diagnose what was happening in Finland, I've talked to Andrew Winters about this, we have this extension of the jet and we're seeing a lot more moisture. So you have really different large scale mechanisms, but then ultimately the amount of water vapor seems to have some agreement in what happens with the microphysics, at least at these 2 sites. I have to caveat, we have over 10 years of data, but it's still 2 sites. So we were really surprised at how much agreement we saw, and we were expecting kind of different size distributions of the particles, but actually the AR and no AR have really similar distributions of particles. It's just you have more when the ARs. We thought it would be narrower or wider, but it's not so much that. It's that you have more and they're denser.
Yeah, well, I guess you already kind of hit it, because I was sort of curious when you showed those AR versus non-AR. You know, I thought that was pretty significant, that difference. And I guess it sort of had that question you had, especially with Marquette, thinking about, when you think of an AR, it's a very far synoptic scale.
It's huge, yeah.
But you think about places like Marquette, which is gets a lot of snow, smaller mesoscale across the lake. I wonder, can you see the fingerprints of that different? Like if you were, especially maybe if you were breaking down, on a case by case basis as opposed to like a mean, something you see.
Yeah, great question. It kind of has led to our research. It's kind of related. I mean, mesoscale processes are different in the Great Lakes, but it kind of has led to this research. How much is like the fingerprint from the large scale, like really like you use fingerprint, how much is that, the big lever, versus the mesoscale modification? So we will have some ARs that reach Marquette, but maybe they go to the side and then they come back and become these enhanced lake effect, like probably the convective stuff you're looking at. So trying to tease out, and I was just talking with Angela and Mary and Sarah, trying to tease out all these multi-layers of what's the large scale signal versus mesoscale that's coming out in the microphysics is really interesting. I think it's really complicated. I start out with this caveat of these are very rough categories, and now we can delve into these details. But some of the things that Jack and Alana found, for example, kind of lead us in a good direction to start kind of cutting them up more, right? Yeah, thanks.
Thank you for an amazing presentation there. Actually kind of following up on what you just said. And maybe you said this, but I missed this, but I'm wondering how the identities of the AR losses showed that larger particles sizes. Other one, how does that add to the mode of precipitation? Generally, does it matter? And do you have a sense of how different reanalysis data sets are? Do they include those kind of things, or how does that affect that precipitation?
Yeah, good question. I think what Jack and I were surprised by is that it seems that the more higher rates we get, that more water mass that we're getting from the snowfall seems to be just that increase in that big increase in particle number and that slight increase in rhyming or density, We thought that we'd have more large particles, and we didn't really see that. We saw we had overall number density was higher. The other question you had about reanalysis, reanalysis is an awesome tool. I use it all the time. When it comes to cloud and precipitation, you're averaging over a pretty big grid space, right? And it could be getting things correct or incorrect for right and wrong reasons. I think it's really important that we do these studies that incorporate observations and reanalysis, or think of reanalysis from these physical, perspectives, and being able to understand, if the reanalysis is consistent with the precipitation physics. And so especially in the polar regions where we're really observationally poor, right? We don't have many observations there. So then now you're interpolating and making assumptions across a bigger area where maybe the models aren't capturing some stuff. I don't know. I don't want to say don't use reanalysis. It's a super important tool, and it's a great tool to look like. All of my students use that as part of their kind of large scale perspective. Whether it doesn't always make it to the paper, but we really need that to better understand it. Yeah, thanks.
Great talk. When you try to differentiate between AR and non-AR and trying to find the characteristics between the two, how much can you differentiate between AR enhancement versus perhaps maybe just higher frequency of convection within space?
Yeah, no, it's a great
How do you
question.
disseminate between those two, and then maybe more philosophically, does it even matter?
Yeah, I don't know. I've talked with the snowfall people I work with, you know, like a lot of the plots I showed in ARs, we see this enhancement over the ocean so we can like eliminate topography. Like I'm trying to eliminate factors to get, but I think a lot of it's, we're seeing some big convergence and we can't always separate that stuff out. We need to investigate some more of these tools. I think a lot of that's convergence. And I will just say, even though this talk was a lot about ARs and I think it's a great statistical tool, I don't think it's the only tool. And actually Jack and I are looking at a lot of stuff with the airborne ops where we're looking at water vapor transport, but we're also looking at these large scale factors that really matter too. So it's a great question. I don't think they're decoupled. I think, you know, it's further investigation where we can dig into that, and I think it's really needed and important, and this is something where a group is actively looking at, which is, again, we're trying to start with that and say, oh, we have some evidence, like exactly what you said, and so we're starting to see what tools we can use to dig into that, yeah.
We'll take Larissa and John, and then we'll put.
Yeah, I was gonna ask something related, which
Yeah.
is like you focused on the thermodynamics a lot, like the amount of moisture, but is there also ascent in terms of the dynamics, which I think is
Yeah,
what you're getting at,
I mean,
right? So-
I would love to talk to you more, anybody here, and I've been talking to Andrew Winters about this too. I think there is a lot of indicators, you know, the nice thing about looking over ocean is we can control some factors. Looking over the Greenland ice sheet at the very top on the plateau, we have a bit of control too, but I think there has to be, and I'm not sure the best ways to diagnose it. We've been looking, Jack and I have been looking at various omega and other parameters of convergence and like kinetic energy to try to figure this out. And like I said, I'm not totally married to ARs because everything gets smeared. If you have atmospheric blocking, it could be cyclones, it could be ARs, it could be all these different things. And the dynamics is this important part that we want to dig into. One thing that I've talked to Andrew a lot about, and I want to talk to folks about more who are dynamicists, is this deeper, warmer layer we see. We see a much deeper tropopause, and we're seeing this much faster upper level winds, and this indication that we have this extension of the jet during these events. So how much is it just that versus, so I think it's totally a good question, and it's something we really want to dig at. And you know, when we saw this in Greenland, this increased tropopause height and this extension of these upper level winds, we're trying to like figure out ways where we can link that to like dynamic processes and figure out what's going on there. So great question. It's something we really want to look into. We want to partner with some dynamics people to diagnose this. Yeah, thanks.
Yeah, I think it's along the same lines. I was thinking the same thing. You know, Kyle's got this really nice way of identifying the atmospheric rivers that you showed. Why not color them in with 700 millibar omega?
Yep.
So that you know what it looks like in each individual river, or maybe even 850 temperature or something.
Yeah.
Because it might be your June, July, August events. They just don't find the poleward displaced temperature contrast that they found usually in the other 3 seasons.
Interesting.
You know, and you get the same kind of, not exactly the same, but a reasonably similar structure to the rivers
Sure.
themselves, but they find that background baritonicity in the 3 seasons. They can't find it too far north.
Yeah.
So there may be things like that that are easily applied or imposed upon
Yeah.
the AR identification scheme.
No, I love that.
Color it in a
And
little bit.
yeah, so Jack's been doing kind of like along the lines you guys suggested. He's been taking these contours and then coloring them by like things like omega at various levels. And we've been looking at temperature perturbations at those levels too. So we're digging into this, but I'd love to talk to you more. Whenever I see Andrew, so he came up to Steamboat, we had this long session where we talked so much about jet, and I really want to figure out the right tone working, and I can write something together and dig into this more. So I appreciate it. I really want to. Yeah, so we're starting to explore it. We definitely know it's an important factor. We're trying to piece that out. Yeah, thanks.
Sounds good. If I know Claire well, then if you want to keep talking to her, you can probably convince her to go to a bar somewhere. Otherwise, we'll be here tomorrow as well, briefly. But let's give her another hand.